Aloha everyone, this is our Ike Wai project. Our mentor was Dr. David Garmeyer, and our group members involved Ricky Choi, Alexandra Myers, Ian Umetsu, Taylor Pave, Tian Tran, and Taylor VT. Hawaii depends almost exclusively on groundwater. The Ike Wai project is about modeling Hawaii's fresh water to avoid future problems such as shortage and contamination. This figure displays a map of the numerous water wells that are located just on Oahu alone. There are many water wells located around the rest of Hawaii as well. The problem with today's water sensors typically are they're either very expensive, contaminate the water sample, or are prone to degradation. These traits are undesirable for a stationary water monitoring network. To remedy this, our solution was to design a water monitoring system that will observe Hawaii's freshwater behavior. The sensor will measure flow rate, pressure, temperature, and turbidity. The water monitoring system will be placed at the water well sites on Oahu and on sites in America Samoa. The words Ike Wai are to understand the fresh drinking water, shows what our goals are for this project. For this project, we would like the water monitoring system to be planted at each water well. A motor controlled by a pre-programmed Raspberry Pi will then descend and ascend the sensors embedded into a custom cable in the well. Then, the Raspberry Pi will then wirelessly transmit the data to a water monitoring home base. Each water monitoring system will be self-sustaining with solar panels. This picture shows an early version of the system. For our system, we needed photovoltaic solar panels, 3D printed PETG cables, acrylic housing, and a stepper motor-driven winch. For the capacitive salinity sensor, we needed magnet wire and PCB electrodes, and PDMS for electrical insulation. We also needed to know how to CNC laser cut plexiglass and CNC milled circuit boards. The figures on the right show the custom print heads for the 3D printed PETG cables. For our results, for salinity sensors, we were developing interdigital and parallel wire sensors which could measure salinity from dielectric parameters. The capacitance value is converted to a voltage signal using an op-amp differentiator, which outputs to a differential amplifier for noise rejection. Current challenges include optimizing the detectable salinity range and constructing mechanically sound sensor mounts. The figure you see is a graph of the sensor output versus our salt concentration when testing the salinity sensor. For our off-grid power system, to make the system sustainable while minimizing energy use, we installed 10-watt solar panels and voltage controllers to power and regulate the system. For the case of minimal sun exposure, we calculated that we would use a 12-volt battery that will sustain a system for up to 3 days. For the tether cable fabrication, using a MakerGear M2 3D printer, we also created custom print heads in order to fabricate tether cables using 38-gauge copper magnet wire and PETG 3D printer filament. By using a stepper motor-driven spool for automating the collection of the resultant cable, the machine is capable of fabricating long spans of cable with minimal operator intervention. For our future research, we hope to modify sensor design to extend the detectable salinity range and also to configure the Raspberry Pis to measure and collect sensor data. We also would hope to fabricate a set of 10 rapidly deployable well monitors kits and design and fabricate PETG sensor housing. We would like to thank NSF EPSCoR program, the UHM, REU, and Europe programs, Chris Schuler and Dr. Ali El-Kadi, and also Dr. David Garmeyer for their support and help. Mahalo, and thank you for watching.